In this video, I want to get a little bit deeper into the concept of limits. And the way I'm going to do it is I'm going to state the main, probably 11, 12, or whatever, of the main limit laws. And then I want to work some problems where we actually put them to use. I want to try and show you the correct ways to use these laws and how to avoid some of the pitfalls. So first of all, first and foremost, I just want to go ahead and state these laws. All right. So some assumptions we're going to make before we state or use these laws. All right. Number one, C is constant. So we're going to use the letter C to represent some arbitrary constant. Also, the limit of f of x as x approaches a, and the limit of g of x as x approaches a, both exist. All right, so what that means is that this limit doesn't equal infinity, or it doesn't equal negative infinity. This limit doesn't equal infinity, and doesn't equal negative infinity. What this means is that both of these equal actual numerical values. Because when you say the limit equals infinity, you're not saying it exists. You're specifically expressing in what way it failed to exist. When you say a limit equals negative infinity, same thing. You're not saying it exists. You're talking about how it failed to exist. All right? So, again, C is a constant, and both of these exist by that meaning they equal numerical values. If that is all true, under those circumstances, here are your limit laws. Number one, the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. There's your first law. Second, the limit as x approaches a of f of x minus g of x equals the limit as x approaches a of f of x minus the limit as x approaches a of g of x. Law number two. Number three, the limit as x approaches a of a constant times f of x is equal to that constant times the limit as x approaches a of f of x. This is basically saying up here that the sum of limits is the limit of sums. This is saying that the difference of limits is the limit of differences. And this is saying that a limit of a constant times a function is a constant times the limit of the function. This basically means that constants just can be moved out front. Okay, constants just can be popped out front as is convenient. All right. Next, limit as x approaches a of f of x times g of x equals the limit as x approaches a of f of x times the limit as x approaches a of g of x. This is saying that the product of limits is the limit of products. And last one for a minute. Limit as x approaches a of f of x over g of x is the limit as x approaches a of f of x over the limit as x approaches a of g of x. This is true. This one has its own disclaimer. All right. This one is fine. This one works. This one is true as long as the limit as x approaches a of g of x is not equal to 0. All right. Remember, you can't divide by 0. That's pretty much a universal truth when it comes to mathematics. It applies to limits as well. All right. So there's your first 5 most basic limit laws. These are the ones that get used quite a bit. But moving on, and before I jump into examples, I want to express them all because there's sort of a theorem I want to state before I use any of these laws. Law number 6, limit as x approaches a of f of x to a power, to the nth power, equals the limit as x approaches a of f of x with the entire thing being raised to the power. Power of limits is limit of powers. 7, limit as x approaches a of a constant is equal to a constant, and limit, we'll just make this number 8, as x of x as x approaches a equals a. All right. These two put together with number 6, 7, and 8 put together allow us to take the limit of lots of different things. As a matter of fact, if you use 6, 7, and 8 together, you get number 9. So 9 really doesn't have to be stated. It's actually already subtly, but already covered under 6, 7, and 8. But the limit of x to the n as x approaches a is a to the n. So again, as you can see, they're using 8 and 6 together to make this happen. So that's not something all by itself. As a matter of fact, with number 10, you have the limit as x approaches a of the nth root of x is equal to the nth root of a. And with that one, they're using 6 and 8 together. And of course, with this one, because roots are involved, there's an assumption involved. And that is that if n is even, if n's an even number, if you're having an even root, we assume a is greater than 0. So we're assuming that we're not trying to take, say, like the square root of a negative number. Okay, so we're not going to try and justify that. And for, I believe, the last one for a while, the last one, they're going to use 6, 7, and 8 all together again to claim the limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. So once again, they're using the previous ones for this one. So by that I mean this one pretty much is already taken care of. It's already covered. It doesn't have to be individually stated. The others already account for it if you realize that the nth root is nothing but a form of a power. Roots are nothing but fractional powers. So 6 and the statement in number 6 takes care of this one for us. All right? But they felt like saying it anyway. That's okay. So let's work a few of these limits. All right? What they're going to have you do on the first few is stretch them out in the longest way possible. You're going to want to stop doing that really soon. All right? But for now, here's what I'm talking about. Let's see if we can make a limit problem last as long as possible. A limit as x approaches -2 of 3x to the 4th plus 2x squared minus x plus 1. All right? And when I say stretch it out and make it last as long as is humanly possible, here's what I'm talking about. All right, this is going to be equal to the limit as x approaches -2 of 3x to the 4th plus the limit as x approaches -2 of 2x squared minus the limit as x approaches -2 of x plus the limit as x approaches -2 of 1. All right, so that's the way they want you to do it first. What have I used? What has enabled me to do this? I've so far used rules 1 and 2. Sum of limits is limit of sums, and difference of limit is limit of differences. So I've used 1 and 2 so far. Next, This is equal to the limit as x approaches -2 of an x to the fourth with a 3 out front, plus the limit as x approaches -2 of x squared with a 2 out front, minus the limit as x approaches -2 of x, plus the limit as x approaches -2 of 1. So what I did is I took the constants and I tossed them out front, moved them out of the limit notation. What has allowed me to do that? Rule number 3 has allowed me to do this. All right? Then I'm going to say this is 3 times the limit as x approaches -2 of x to the fourth power, plus 2 times the limit as x approaches -2 of x, entire limit to the second power, minus the limit as x approaches -2 of x, plus the limit as x approaches -2 of 1. So what allowed me to take those powers and move them outside the limit notation? Well, that's rule number 6. All right? So now I can say that this is 3 times, and limit of x as x approaches -2. Okay? Well, that's rule number 8. Right? That's rule number 8. So this becomes a -2, -2. This is rule 8 again. This becomes a -2, rule 8. And that's the limit of a constant. And the limit of a constant is just that constant. And that was rule number 7. Okay? So now I have used, I would not say all, but quite a few of the limit laws. Now I can just evaluate things, well, like you normally would, right? For example, a -2 to the fourth power is a 16. -2 squared is a 4. Minus a negative makes plus a positive. And 16 times 3 is a 48. Oh, off the page. And 48 plus the 8 plus the 2 plus the 1 gives me a 59. All right. Now, was that long? Oh, you bet it was. Calculus problems can be. It is their nature. All right. But is there anything in here that would allow me to get things done in a slightly faster fashion? Yes. All right. So what I could have done, and what it tells me that I can do, is if f is, number 1, a polynomial, or number 2, a rational function, okay, with a in the domain. All right, so with your rational functions, we have to make a domain statement. With your polynomials, we don't have to, because polynomials have for their domain all real, so no domain statement needed. So what this will tell us is that the limit as x approaches a of f of x would be f of a. All right. Now, I said the other day in one of our first lectures on limits that when you're taking a limit, the last thing you care about is what the function equals at that number. Well, that's still true. May not seem like I'm sticking to that statement, but I am. It just is the case that under these circumstances, those two values happen to be the same. All right? That's all it is. So, in this problem, where I drew it out into 100 different steps, I could have just looked at this and said, this is a polynomial. This is a polynomial. Therefore, this will be equal to 3 times -2 to the fourth plus 2 times -2 squared minus a -2 plus a 1. And I could have cut through all of this straight down to the 59. All right, so there are your limit laws. All right, now again, it specifically said those limit laws can be used as long as f of x and g of x, their limits are defined, they exist, and the limit on the denominator is not 0. Okay, it is not 0. All right, so for example, then limit is x approaches 1 of a x squared plus 1 cubed times a x plus 3 squared. All right, what I would do is I would recognize this polynomial, therefore the limit exists. Therefore, this would be nothing more than a 1 squared plus 1 cubed and a 1 plus 3 squared. This is a 2 cubed times a 4 squared. 2 cubed is 8. 4 squared is 16. And after that, all you have to do is the product. 8 times 16 is a 128. Okay? Did not have to go through endless steps. Okay? This works for both overall limits. This works for left-hand and right-hand limits as well. Again, as long as it is defined. As long as it is defined, it works. As long as it's defined. Now, here's what you're going to run into. You're going to run into things that are defined or that have a 0 in the bottom. So, for example, limit as x approaches 2 of x squared plus x minus 6 over x minus 2. All right? So what you're going to see is you have a polynomial on the top, so you should be able to just plug in directly. You have a polynomial on the bottom, so you would think, well, I can just plug in directly. But if you plug into this polynomial, you get a 0. And we specifically said you can't just plug the number in when you have the 0 in the bottom of a fraction. So in this section, you're going to learn 2 or maybe 3 of the first tricks that you use to evaluate a limit when you can't just plug and chug, as it's commonly called. When you just can't plug the number in, what do you do? Because if you plug in right now, you get a 2 squared plus a 2 minus a 6 over a 2 minus 2. 2 squared is 4. 4 and 2 is 6. 2 minus 2 is 0. Right? So with this, we get a 0 over 0. When you get a 0 over 0, what that means for us, at least right now, is we have no idea what that limit's equal to. 0 over 0 for us right now is a great big mystery. It's a red flag, you might call it. It tells you you don't really know what's happening here. All right? So the general rule is, when it comes to limits, you can do any algebra you know how to do, you're allowed to do before you take the limit. So let's see if there's any algebra. Let's see how much algebra we know. I'm going to take the limit as x approaches 2. Then x minus 2 on the bottom. So trick number 1. Please remember you know how to factor. Right? Please remember you know some algebra. And factoring is one of the things that you know. This numerator will factor x and x makes x squared. 3 times 2 makes a 6. Plus a 3 minus a 2 gives you the plus 1x in the middle. Okay? I haven't done any limits yet. I can do limits last if I want to, and that's exactly what I choose to do. All right? I'm going to do all my algebra first. My algebra says these things cancel. So this will be equal to the limit as x approaches 2 of an x plus 3. Now there's no longer a fraction. Now there's no longer a problem with dividing by 0. This is nothing but a very straightforward, very simple polynomial. I plug and chug, and I get a 5. So trick number 1, factor and reduce. Remember it. Use it. Factor and reduce. Let's try it one more time. Let's say I had the limit as x approaches 1 of an x cubed minus 1 over an x squared minus 1. Once again, notice if you just plug in the 1, you get 0 over 0, which means we have no earthly idea what in the world's going on with this limit. It could be about anything. So, again, remember, folks, you know some algebra. The numerator factors as x minus 1 times x squared plus x plus 1. And if you don't remember how to factor a difference of cubes, I suggest you go figure it out. Go look it up. The denominator factors is x minus 1 and x plus 1. Okay? Algebra says those things can cancel. All right? So this is the limit as x approaches 1 of x squared plus x plus 1 over x plus 1. I can plug and chug now. I can just plug in that 1 because I have a polynomial over a polynomial, and the 1 on the bottom does not equal 0. So there's your limit. All right? So again, trick number 1, factor and cancel. All right? Next trick, next technique. All right? If I had the limit as h approaches 0, and we need to be aware that x is not the only variable in the world, so let's use something different. And here I have the square root of 1 plus h minus a 1 over an h. If you plug the 0 in right now, if you just plug in a 0 blindly, you'll get 0 over 0. Once again, meaning we don't know what's happening here. This is a big mystery. You don't know what's going on when you get a 0 over 0. So, algebra. All right? And this time, it's not factoring. Okay? I'm not going to use factoring. I'm going to use a conjugate. I'm going to multiply both top and bottom by square root of 1 plus h plus 1. All right? Now, the bottom part of this, I'm not going to factor. Right? And how do I know that? Experience is how I know that. It's something you'll learn. I'm not going to multiply that out. The top I will. First times first is square root times square root. Out comes the 1 plus h. Inner product is a minus square root of 1 plus h. Outer product is a plus square root of 1 plus h. Last times last is a minus 1. Okay? Watch carefully what happens. The minus square root and the plus square root cancel. The plus 1 and the minus 1 cancel. What are we left with? What do we still have? Well, we've got the limit. As h approaches 0. On top, there's nothing but an h. On the bottom, there's an h times the square root of 1 plus h plus 1. The h is canceled. That leaves us with the limit. H approaches 0 of 1 over square root of 1 plus h plus 1. Now, notice that when you plug in the 0 for h, you don't get a 0 on the bottom. You don't get the dreaded 0 over 0. All right? What you get is a half. Plugging now gives you a 1/2. And you know that that's a legit answer. You know that that'll work simply because you didn't get any of the, you didn't hit any of the red flags. Okay? None of the red flags. And again, right now, our main red flag is division by 0. All right, so you can use factoring, you can use conjugates. There are some problems where you could use either one. You could potentially go either way. All right. All right, so there's trick number 1, factor and reduce. Trick number 2, use conjugates. All right, you need to learn to spot these problems and know when to use which technique. All right. Trick number 3, technique. Probably shouldn't call it trick. Technique number 3, how do you deal with absolute values? The limit, as x approaches -6 of a 2x plus a 12 over the absolute value of x plus 6. All right, when you see absolute value in there, what you have to remember is absolute value can be defined in several different ways. All right, let's sort of recap that. Absolute value of x, what does it equal? Well, there's actually two possibilities. Absolute value of x equals x, and x is greater than or equal to 0. Basically saying when x is not negative, absolute value of x equals x. It equals the opposite of x when x is negative. All right? So, keeping that in mind, here's what I'm going to do. My first step would be limit as x approaches -6 of, up here I'm going to pull out a 2. Again, don't forget, you know algebra, don't forget, you know how to factor. All right, now you may be looking at this saying, oh, wait a minute. If I could just cancel, well, you can't cancel it with it written like that, but here's what you can do. You can take the limit, you can take this limit and break it up into its left-hand and its right-hand versions. All right, let's see what happens when we approach -6 from the right-hand side, all right? By that I mean, let me draw a picture here. -6 is here. We're coming in from this direction. We're coming in from -5 and -4 and -3, et cetera, et cetera, et cetera. All right? And what you discover is that when you're coming in from the right-hand side, all right, x plus 6 is positive. All right, coming in with -3s, -4s, and -5s, this expression is positive. So when you come in from at -6 from the right-hand side, this is a 2 x plus 6 over x plus 6. All right, when it's positive, in other words, the absolute values can just go away because they're not doing anything. Well, they will cancel. This becomes a limit of a constant. So it turns out to be a 2. Now, if we look at the limit, as x approaches -6 from the left-hand side, that's a 2 over an x plus 6 over, what would it be over? Well, as you approach -6 from the left-hand side, you're approaching it from numbers like -7, -8, and so on. And in those situations, x plus 6 is negative, all right, like we stated here. So coming in from that side, absolute value of x plus 6 becomes the opposite. It becomes the opposite of x plus 6. Well, this time these cancel, but they leave behind a negative sign. Okay, so what I've just discovered is that the left-hand limit and the right-hand limit are different. Therefore, the limit, as x approaches -6, of 2x plus 12, going back to the original, over absolute value of x plus 6, it does not exist. Its left-hand limit existed, its right-hand limit existed, but they did not equal each other. So they overall do not exist. Okay? They do not exist. So there's just a few limit examples for you, hopefully enough to get you started on the limit law problems.